All right, everybody, we want to look at unit vectors. What's a unit vector? A unit vector is a dimensionless vector that points in the positive direction along a coordinate axis. It has no units, and its only purpose is to specify direction, which means its only purpose is to point. That's all it does. Now what I've drawn here is I've drawn a three-dimensional coordinate system. There's the positive x-axis to the right, the positive y-axis is up, and the positive z-axis is actually out of the page, but to draw it on a two-dimensional flat surface I have to draw it at this angle. Now this is a right-hand coordinate system, and it works like this. Okay? The thumb points in the positive x direction, the first finger points positive y direction, and the middle finger points out of the page in the positive z direction. Now when we do this, we don't use x, y, z. We use unit vectors I hat, j hat, and k hat. Now here's what they look like when you draw them. I'm going to draw them right along the axis here. I don't know how easy they will be for you to see, but that vector, that's I hat. It's a cursive I with a little caret on top of it. All it does is point along the positive x-axis. So along the positive x-axis, we have the unit vector I hat of a right-handed coordinate system. In a similar manner, along the positive y-axis, I'm going to put it in here, that's the unit vector j hat. Looks like that. Okay, and so along the positive y-axis of a right-handed coordinate system, we have j hat. And coming out of the page towards you, but we have to slant it because we're on a two-dimensional surface, you see the unit vector k hat. So along the positive z-axis in 3 dimensions, in a right-handed coordinate system, that is k hat. So we have I hat, j hat, k hat. And once again, this is a dimensionless vector, and all it does is point in these 3 directions along a right-handed coordinate system. Unit vectors are always associated with a number. Okay? And let's look at an example. Let's draw ourselves a number line and do a couple of position vectors. There's the x-axis, which could be along the floor, a number line along the floor in the room. This would be the origin at 0 meters. Let's put in 1 meter. Let's put in 2 meters. And along the negative part of after the origin to the right, actually to the left, let's put in -1 meter. And now what's I hat look like in this context? Well, it looks like this. It's a dimensionless vector that points in the direction of the positive x-axis. So that's what I hat looks like. That little green vector, you can see the color. Now, if we have a person who walks from the origin, like so, and this person walks out to about right here along this number line along the floor in the room, we can draw their displacement or change of position. That vector would look like this. It would be a vector that starts here and ends right where the person stops walking. And this vector, it's in between, it's 1.5 meters. It's halfway between 1 meter and 2 meters. So the displacement from 0 meters to the right to 1.5 meters, we write it like this. It would be 1.5 meters I hat. That's how you do it. This is the magnitude. I hat is the direction along the positive x-axis. Now let's suppose we have a second vector. Let's draw another example below that. Let's suppose this time our walker is initially come down here like this. They are standing right about here at 2 meters, and they walk back to -1 meter. So they walk back this way, and now this vector, this displacement vector, which is the change of position, looks like this. Okay, I know you can't see that. Let's scoot it up. Sorry about that. So this is the displacement vector from 2 meters to -1 meter. So this vector would be -3 meters I hat. And again, this shows you that we actually move 3 meters to the left, and the positive direction is I hat to the right. Okay? So these vectors have two parts. Unit vectors have two parts. One, you have a vector component. Now we know what components are. We have x, y components, okay? In this case, the component is it's positive or negative because it has directional sense. And as you can see, this was positive 1.5 meters to the right. This one, its component was -3 meters, which was a displacement or walk to the left. Okay. The second part you have in this two-part scenario is you have the unit vector that tells you what axis you're dealing with: I hat, j hat, or k hat. Now, if we take this vector component, everybody, and if we take what's called the absolute value, okay, we write it like this: the absolute value of the vector component, which means we basically drop the sign, and what that leaves us with, basically the magnitude. And that's a fancy word that means the size or the amount. Okay? So when we take what's called the absolute value of a vector component, we get the magnitude. And the magnitude, well, if you take the absolute value, the magnitude is always positive, and it's considered a scalar. S-C-A-L-A-R. Just magnitude. So in other words, what we're doing when you take the absolute value of a vector component, you are dropping the directional sense. That leaves you with a magnitude which is always positive and therefore a scalar. Okay. That's the very, very basics. Now we need to talk about a little bit of theory here. And there's a bit that we need to look at. Okay, so this is just a warm-up on some theory. We need to look at some of the basic unit vector, call it algebra if you will. Not hard, but we gotta hone in on it so you have an inkling of what it is you're messing around with or getting into. So everybody, we're going to just adjust my paper here slightly and see if we can move on. We want to look at this point at what we call unit vectors in 2D and 3D. Okay? And I think I'm going to stop this and we're going to do this as a second video. So just the introduction here is long enough.